and only up to representation theory. Groups plus Galois, but no torsors, nor the things that I'll talk today and on Tuesday. Okay, so today and Tuesday I want to do some more general stuff. But before that, so let's deal with some issues. At least let me ask the question of something that appeared in the previous two classes. One was we had this category of torsors, and we had this other category of functors. And here there was this issue whether or not in this category we should consider humps to be just morphisms between these functors and natural transformations without any condition, besides being compatible with the structures that these functors were compatible with, or we should consider the set of isomorphisms. If you have any category, then you have a subcategory where you just restrict your morphisms to being just isomorphisms. And that's always a category. And since this category here of torsors, right, so I want to have an equivalence of categories between these two. So landed anyways here, because here any morphism was an isomorphism. Then, well, the question is, should I consider this category or this category to be the target, to have an equivalence? So in principle, then I'd say, okay, fine, then it's better just to consider this one with target just isomorphisms. But the thing is, so then you may ask the question, so if I only land on this one, is it still true that this category, where your morphisms are only isomorphisms, is equivalent to this category, where you consider all morphisms or natural transformations between these functors? Because if this category of torsors is equivalent to this category, and this category is equivalent to this one, then that's it. I mean, these functors and torsors are the same. Okay? So, of course, this category is a subcategory of this other category. So to have it to be an equivalence of categories, for these two guys to be equivalent, then you would want any two objects in this category to be, well, any object in this category to be isomorphic to an object coming from here, which is true. Right? So, but what you need is to have a fully faithful embedding. What you need is that any two objects are isomorphic. So whenever you have a morphism between any two objects, then you would want to have an isomorphism between these objects. Because if that happens, then these two categories will be equivalent. And the question, therefore, is, if I give you two functors that satisfy these conditions, in particular, let's say, for example, that you give me this forgetful functor O. I don't remember if I used that letter or this letter, but it doesn't matter. So this is the functor that sends the representation V to V itself as a vector space. And you have another functor F. Does there exist an isomorphism? Namely, do you have for every representation V an isomorphism like this? And notice that you do have this isomorphism in the cases where V is 0 and the case where V is the trivial representation. Because in both cases, you're forced to have here 0 and to have the trivial representation. So you do have that isomorphism naturally. But the question is it true in general? So if you have a functor that goes from the representation category of a group to vector spaces and commutes with tensor products, direct sums, zeros, and identities, is it true that you have these isomorphisms for every representation V? These linear isomorphisms. Sorry? This f is one object in this category of functors from, so remember this category of functors was the category of functors from G mod to rep G. I'm sorry, to vector spaces. And the question is, if I give you such a functor, an arbitrary functor, that preserves tensor products and direct sums and so on, is it true that for any representation V in G mod, do you have an isomorphism of vector spaces? So this is a linear isomorphism between the vector space V and f of V. If you have that, then it doesn't matter if you choose humps or isomorphisms, which was the issue that we had last time. And then I asked that question. I mean, is it true that for any representation V, do you have a linear map and linear isomorphism? Naturally. So in particular, for example, is it true that the dimension of f of V is the dimension of V? Just by imposing I understand, but as a first approximation, you would want the dimensions to be the same if you want to have an isomorphism. So, but the question is it true that you have such an isomorphism? So that could be a nice exercise to check whether or not you needed to ask for your natural transformations to be isomorphic or not. So I'll ask this question and I'll leave this question open. So does there exist this isomorphism for any functor in this category? And that solves all of the issues that we had last time. If you can't solve it by Tuesday, then ask me, and I'll let you know. All right, so today and Tuesday, I wanted to talk about some other general stuff in representation theory that's not going to come in this test next Thursday. But there are other objects that you might want to study with representation theory. Different types of algebras and different types of groups. So let's start with some of them. So for example, a Lie algebra. And then I should start with groups and then Lie algebras, but then let me start first with Lie algebras. So Lie algebras are, so you fix a field K, and let me ask this field to be of characteristic different than 2 and 3. 2 and 3 are special characteristic for Lie algebras. Then a Lie algebra over K is a K vector space G together with a linear map bracket that goes from G wedge G into G, satisfying the Jacobi identity. The Jacobi identity is that the bracket of A with B and C is equal bracket of A and B. So I'll write it in this way first, and then I'll write it in a different way. So examples of Lie algebras. Well, there are many types of examples. The canonical example is given a vector space V, then G is GL of V. As a vector space is the endomorphism, consists of endomorphisms, k-linear endomorphisms of V. And the operation, the bracket of two endomorphisms, is the composition minus composition is the other way around. So here X and Y are endomorphisms. More generally, if A is an associative algebra, then you can take G to be A. So typically it's denoted like something like this, like A Lie, or probably A minus, but this as a vector space is just your algebra A, but the operation in G is, again, the multiplication minus BA. So if A was commutative, then G with the zero bracket satisfies this condition. So any vector space with a zero bracket is a Lie algebra. So that's the analog of having a commutative algebra. Then this is a Lie algebra. In fact, well, you can check this explicitly. So clearly this is well defined on G wet G, namely skew symmetric. BA is minus AB. And now we just need to check this identity, which is the Jacobi identity. And therefore, okay, I'm not going to write, so I'm going to say the left-hand side and the right-hand side of this identity. So the left-hand side of this identity is A times the bracket of B and C minus B and C times A, which is ABC minus ACB. The parentheses are like this. And here minus BCA plus CBA. So this is the left-hand side of the Jacobi identity. And the right-hand side has two terms. So let's write both of them. So the first one is, well, this is always the bracket of AB, C minus CAB, which is ABC minus BA, C minus CAB plus CBA. So that's the first term here, and the second term is BAC minus ACB, which is BAC minus BCA plus ACB, minus ACB plus CAB. So hopefully I did this right, and this should be this plus this. So ABC here is equal to this one by associativity. And I need there that A is an associative algebra. ACB here with a minus sign is equal to this, again, by associativity. BCA is equal to this by associativity. Both of them have a minus sign. And CBA is equal to this by associativity. On the other hand, BAC here comes with a different sign here and here. Both of these are on the same side of this equal sign here. And this one here comes with a different sign than this one. In each cancellation, I needed associativity. Okay, so the Jacobi identity holds, and that's a Lie algebra. A nice exercise is the following. Let's suppose that you have a vector space A. Let's suppose that you have an algebra, but not necessarily an associative algebra. Let A be an algebra. So this just means that you have a bilinear map from A tensor A to A that you call the multiplication. Doesn't need to have an associativity condition. So then the associator in an algebra is a map from the A tensor A to A, which is simply ABC minus minus A BC. And I'll call this the associator. So let's choose a letter let's choose this letter. And this is a trilinear operation. So now A is an associative algebra when the associator is the zero map. Okay? But A is a pre-Lie algebra or a right symmetric algebra. And I reserve the right to get this name wrong. Probably this should be called left. I never remembered these things. A is a right symmetric algebra. Probably respectively left symmetric algebra. If A of A, B, C is equal to A of B, A, C for every A, B, C. So the associator might not be 0, but if you exchange A and B, you get the same value. And it's a left symmetric algebra, respectively. So probably I exchanged left and right in the definition, but it doesn't matter. A of A, B, C is equal to A of A, C, B. So you exchange the last two terms. Okay. So the exercise is that if you have either a left symmetric algebra or a right symmetric algebra, that's why they're called pre-Lie algebras, then exercise, if A is a right symmetric algebra, then G is equal to A Lie, which is just the same thing, the same bracket. AB is AB minus BA is a Lie algebra. So the exercise is exactly the same thing. You just use expand, but then the problem is that you don't have cancellations like we had here. You need to just add and subtract terms to get to use these identities to get the cancellation. But whenever you have an associative algebra, you have Lie algebras. Whenever you have a pre-Lie algebra or a right symmetric or left symmetric algebra, you have a Lie algebra. That gives you lots of examples of Lie algebras. So this was one such example, because I started with an associative algebra of endomorphisms of a vector space. You have many more. So for example, if you have, so perhaps 3, if you have, let's say A is a commutative. Well, let's say A is an associative algebra first. Then a derivation of A that I'm not sure if use this notation or perhaps this notation. This is a subspace in the endomorphisms of A. And it's defined, so these are endomorphisms of A that satisfy, let me call D. That satisfies that D of AB is equal to D of A B plus A GB for every AB in A. If A is commutative, then you typically move this B on the other side. So that's what's called a derivation of A. So now, the endomorphisms of A is a Lie algebra with the bracket, because, well, it's just a vector space. And we just proved that the endomorphism of any vector space is a Lie algebra with this bracket here. And then we may ask whether or not the derivations are closed. So the question is whether or not this belongs to the derivation or not. So I'll just check this. What is this? And then this is D prime AB minus D prime D AB. Now, using that D prime is a derivation, this is D of D prime A B plus D of A D prime B minus, now here I use that D as a derivation, dA B plus D prime, minus D prime of A dB. Now again, now use that D as a derivation, and this is D prime of A B plus D prime A dB plus, now we use on the second one that D is a derivation, so we have dA D prime B plus A D prime B. And now these last two terms are minus D prime dA B minus dA dB. And finally, I'm sorry, this is D prime B. And finally, this guy gives me D prime A dB minus A D prime dB. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8 terms, which is good. So now let's see if we have any cancellations. Well, I want these cross terms to cancel. And I see, for example, here I have D prime A dB, and here I have D prime A dB with different signs. So that's good. Here I have dA D prime B, and here I have dA D prime B. So this one also cancels. Okay. And now I no longer have any cross terms. So what I see is that I have D prime A here and D prime B here. So I have D prime applied to A, and then I have also minus D prime D applied to A. So what I have is the bracket of D with D prime applied to A, and everything here multiplied by B. So that took care of this term and this term. And now these last two terms are minus, well, are A with D, D prime B, minus D prime DB. So this is plus A, and here now is the bracket of D with D prime applied to B. So what we see is that if I have two derivations, then their bracket is a derivation. And that's for any associative algebra. Namely, given any associative algebra, we have this Lie algebra with the bracket, and then we have a subalgebra with this, which is a subalgebra of derivations of that algebra. In the particular case where when your space is a manifold, so this example is a particular example, is when, say, X is a smooth manifold, if you do not know what a smooth manifold is, it doesn't matter. Just think of a topological space, and what I'm saying just makes sense anyways. It won't be called that way, but it makes sense algebraically. But if you have a smooth manifold, then you can consider A to be the algebra of functions, of smooth functions on X. So this is an associative algebra. It's also a commutative algebra, but we didn't even need commutativity there. It's a commutative associative algebra. And the algebra of endomorphisms of A is a Lie algebra, which is a huge, horrible Lie algebra. But then inside of the algebra of endomorphisms of A, we have the algebra of derivations of A, which by the lemma which is proved is a sub-Lie algebra. This Lie algebra is called the vector fields in A, the smooth vector fields in A. On X. We just checked that vector fields form a Lie algebra with this natural bracket coming from derivations, from composition of derivations. So what other kinds of Lie algebras do we have? I think I'll just stop for a second right now. Perhaps I'll give you a list of classical Lie algebras. So there's the following list of classical Lie algebras. If you give me a vector space V, and you give me some extra structure in V, and then we'll want to preserve that structure. So for example, remember that we had this functor. Well, no, let's start with the following. Just want to make it as... Okay, so let's suppose that you have a symmetric bilinear form. So we have a pairing. You typically would ask this pairing to be non-degenerate on V. Then you have a Lie algebra, which is called O. It depends on V and it depends on this pairing. Probably I'll write little o. Which consists on endomorphisms. So this is a sub-Lie algebra of GLV. But it's such that AV W plus V AW is equal to 0. So that's preserving this form. Well, you can check that this is a sub-Lie algebra. Let's just quickly check it. So this is a sub-Lie algebra of GLV, which is a Lie algebra with a bracket. These are the orthogonal, well, I'll call this the orthogonal Lie algebra. If you write this in terms of matrices, if you choose a basis such that this product, this bilinear pairing, just has the identity matrix as a matrix, then these are just the skew symmetric matrices. So if you identify this space with matrices, let's suppose that V is an n-dimensional vector space, and if you identify this space with n by n matrices with coefficients in your field K, and you choose this bilinear pairing to have matrix, the identity, so choose a basis, and let's say that this bilinear pairing has this standard matrix, so that's a symmetric pairing, then this subspace of matrices consists on skew symmetric matrices. And they're stable under the bracket, which is trivial. But anyway, so let's just check this in generality. Then I would want, and this is the last trivial check that I do, I want to understand what is this, V, A, B, W. And this is A, B, V, W minus B, A, V, W plus V, A, B, W. Well, let's just minus V, B, A, W. Which is, where are we? Okay, so I'll use that A is, well, perhaps we need to add and subtract some terms. Right? So what I know is that A, BVW is the same thing as minus BVAW. Okay? So probably we want to add and subtract those terms. So I'll just subtract and add BVAW minus BVAW. And then the same thing for this one. I'll just add and subtract AVBW plus AVBW. So this is equal to this. Okay, and now we check that, well, ABVW plus BVAW, this is 0, because A is orthogonal. So this cancels with this because A is in OV. And I'll just don't write this inner product here. Same thing for this one, BAVW minus AVBW cancels because B is in that Lie algebra. And how about the other ones? Well, so this one here cancels with this one here because A is in the Lie algebra, and this one here cancels with this one here because B is in the Lie algebra. Okay? So therefore, this is a sub-Lie algebra. So that's the orthogonal Lie algebra. At no point we needed this guy here to be symmetric. We never used any symmetry on this bilinear pairing. So actually, the same thing works if I just take a form inside of just V tensor V. Yeah, so probably I should say just any map from V tensor V to K. So if you take this map, this bilinear map to be symmetric, you just get the orthogonal algebra. If you take this bilinear map to be skew symmetric, you get the symplectic algebra, and that one is denoted by this. So typically, when you have a skew symmetric map, you will write it like this, and then the corresponding Lie algebra is SPV. And you notice a difference between this S and here that I'm not using S. So let me tell you what S means. Remember, we have a functor from vector spaces of a fixed dimension. Let's suppose that V is of finite dimension. Now, let's suppose that V is finite dimensional. And we have a category of, well, let me do this in, I think I did it here already. So if you have it this way, then for any arbitrary dimension, yeah, perhaps I'll just fix the dimension to be n for a second, and then I'll just only talk about the category of, I'll have a category of one-dimensional vector spaces. Otherwise, if you just want to have arbitrary finite dimensional vector spaces V, then you'll have on this side a category of pairs, a one-dimensional vector space and a natural number. And morphisms in that category, so let's suppose that you have pairs, one-dimensional vector spaces. So this category is going to consist of pairs, one-dimensional vector spaces and a number. So morphisms in these categories are going to be these guys are a morphism between L and L prime if n is equal to n prime or 0 otherwise. Or probably empty otherwise. So there are no morphisms between two spaces that have different dimensions. So then you have a functor from this category to that category. Remember that functor was from V to the determinant of V. And here you just put the dimension of V as the number. And this guy here was the top wedge power of V, which is a one-dimensional vector space. And this was functorial. Okay? All right. Remember that actually this gave you a map. And this map was from automorphisms of V to automorphisms of the determinant. But what happens? So this is inside of endomorphisms of this determinant. And endomorphisms of the determinant, so this is inside of endomorphisms of the determinant of V. This is a one-dimensional vector space. Therefore, the endomorphisms form a one-dimensional vector space. But there's an element in this endomorphism, which is the identity. So this vector space is not only a one-dimensional vector space, is the trivial vector space, is canonically the field. Because I have one element in a one-dimensional vector space, is a basis. And therefore, this guy here is not just an arbitrary group, it's canonically the non-trivial elements of the field. And this morphism here is called the determinant. The fact that this is a group morphism from GLV to invertible elements in your field. But actually, what you have is from GLV into endomorphisms of the determinant of V. Well, probably I shouldn't say GLV. I'll just say end V. Well, because the determinant is multiplicative. So actually, this is a morphism of associative algebras. No, I'm sorry. I just said something brutally wrong. So you have this map, which preserves multiplication. Certainly does not preserve sums. It's not a morphism of associative algebra. But at this level, it's a morphism of groups. Preserves multiplication. Okay, so how about the trace? So that's the determinant. But how about the trace? So the trace is even easier, because what is that of V as a Lie algebra? So this is a one-dimensional vector space. Okay? So an obvious observation is a one-dimensional Lie algebra is commutative. Which of a one-dimensional vector space with itself? An antilinear bracket on a one-dimensional space has to be 0. So therefore, that of V is canonically a commutative Lie algebra. It's a one-dimensional vector space which is canonically a commutative Lie algebra. So we have this morphism from GLV into automorphisms of the determinant of V, which was the determinant of your morphism. The usual, if you pick a basis of V, this becomes invertible n by n matrices. This becomes just the field, and this is the usual formula for the determinant. And, well, now we get a morphism of Lie algebras from GLV to GL, the one-dimensional. I'll just call it like this, GL.V, or if you wish, this is just the one-dimensional Lie algebra. And the bracket is 0. And this morphism is a trace. Namely, this is a map of Lie algebras from GLV to the one-dimensional Lie algebra, and to check that this is a map of Lie algebra, then I need to check that the trace of A and B is 0. The bracket here is the commutator, so this is equivalent to saying that the trace of AB minus BA is 0, and this is the basic property of the trace, that the trace of AB is the trace of BA. Okay? So those are morphisms. Here I'm hiding in the definition that Lie algebras form a category, so let me write here. Lie algebras form a category, and a morphism of Lie algebra is a linear map. A morphism from G to G prime is a linear map. Map phi such that the bracket of A, B, phi is equal to the bracket of phi of A, phi of B. So in that sense, the trace is a morphism of Lie algebras in as much as the determinant is a morphism of groups. Okay, so now, well, I think I didn't define SO as a group. So I'll define first SO as a Lie algebra. Observation, the category of Lie algebras has kernels. Namely, if you have a morphism of Lie algebras from G to G prime, the kernel of phi is a subalgebra of G, is a Lie algebra. This is just trivial. It's the fact that phi of the bracket of A and B, since it's a morphism, is the bracket of phi of A with phi of B, which is the bracket of 0 with 0, which is 0. However, the category of Lie algebras, therefore, A and B is in the kernel. However, the category of Lie algebras does not have co-kernels. Has no co-kernels. In as much as groups The category of groups, remember, doesn't have co-kernels. If you have a morphism of groups, the kernel of that morphism is not just an arbitrary subgroup, but it's a normal subgroup. And the same thing with Lie algebras. If you have a morphism of Lie algebras, the kernel of the morphism is not an arbitrary sub-Lie algebra, it's an ideal. So definition, a subspace is an ideal if the bracket of I with G is inside of I. So you can check that that's a sub-Lie algebra in particular, because the bracket of I with I is inside of I. And the kernel of a morphism is an ideal. This is just easy. Here you needed one of these two guys to be 0 and not both of them. Okay, so more generally, therefore, whenever you have an ideal, if I is an ideal, then G mod I is a Lie algebra. With the bracket being just the obvious bracket that you can write. So ideals for Lie algebras are the analog of normal subgroups for groups. Okay, now that we have this, then we have this Lie algebra GL of V, and we have the trace map to K. Then this is a morphism of Lie algebras we've already checked. The kernel of the trace, so those are the matrices whose traces are 0, is a Lie algebra that is called SLV. And it's sub-Lie algebra. If I restrict this morphism trace to the subalgebra, which is O of V, suppose that now we have a symmetric pairing, then I restrict the trace to this subspace, then the kernel here is called SOV. So those are matrices that are skew symmetric and have 0 trace. Good. Correct. So the question is SOV the same thing as OV? And finally, the same thing for this, for a pairing that is skew symmetric. Okay. All right, so now we have a list of Lie algebras. So let's go now to groups. So definition. Or perhaps, yeah, so let me give you just another definition. Is a representation, let G be a Lie algebra, over a field K. A G module, or a representation of G, is a K vector space together with a morphism of Lie algebras from G to GLB. Morphism of Lie algebras. So this is very similar to what we had for Lie groups, for groups. And you can check that the category of representations of G has kernels, has co-kernels, everything in the trivial way. So this is the analog of the category of representation of a group. It has all the structures that representations of a group has. But it has something nicer. So the first difference that you see immediately is when you want to study tensor products. So for a group G, if you have a representation, well, two representations, oops, the other way around. Let's suppose that V and W are representations of a group G. Then V tensor W was a representation, and the action of an element of a group in V tensor W, we defined it to be GV tensor GW. That's not the case for Lie algebras. So for Lie algebras, you also have that V tensor W is a representation of G, but the action of an element in your Lie algebra on V tensor W, you need to define it to be AV tensor W plus plus V tensor AW. Exercise, check that this gives an action of G on the tensor product. Namely, this defines a morphism from G to GL of V tensor W, which is a morphism of Lie algebras. So why do we care about these Lie algebras? It's because perhaps this is not the best of definitions, but I don't want to talk about Lie groups here explicitly, so I'll talk about algebraic groups. So definition, a linear algebraic group over a field K, but what I'll say it just makes sense over any ring, or just could say it over Z, is a collection of polynomials in n square variables. So the variables, I'll call them x, I, j. I and j is equal to 1 to n. So that gives me n square variables. So here n is a fixed natural number. You give me n square arbitrary variables and give me a bunch of polynomials with coefficients in K, with the following property, such that for any K algebra, well, for any, let me write it in a different way, for any commutative, associative, unital K algebra A. So now you have a bunch of polynomials in some variables with coefficients in K. But this K sits inside of A because A has a unit. Therefore, those polynomials, I can view them with coefficients in A. So it makes sense to look at the collection of elements, the collections that I'll call, I'll define it this way, G A to be the collection of matrices n by n with coefficients in A, such that Fi of G is equal to 0 for every I in I. So I have a bunch of polynomials in n times n variables. If you give me an n by n matrix with coefficients in A, actually this didn't have anything to do, well, it doesn't matter. I can evaluate my polynomials in those n by n coefficients. That's a commutative algebra. If I get 0, well, then I just declare that matrix n by n to be in here. So I'll require two things about this. First of all, that this is invertible, that those matrices are invertible. And second, that this is a subgroup. That's a definition. So I'm still defining what a group is. Right? So a group is a bunch of polynomials, but not just arbitrary polynomials. They need to satisfy the following condition. Whenever you give me a commutative algebra, you write down the set of zeros of those polynomials, and every matrix that is in the kernel of these things, then it's inverted. Actually, no. Let me just change this definition. Let me add the condition here. So this is the collection of matrices n by n such that G is invertible and is in the kernel. So that now by definition is inside, and then I'll ask this to be a subgroup. And I need an extra condition. So now if you have two commutative, associative, and unital algebras, let's say A and B. So now I have G of B with the same condition. And let's suppose that you have a morphism of commutative associative algebras from A to B. So if I have a morphism from A to B, then any n by n matrices, I get to a morphism to n by n matrices in B. Just apply that morphism to each entry. So I have a map from this to this. And I will require that this map is a morphism of groups. So compatible with this, of course. This is a subgroup of GLA. This is a subgroup of GLB. Here I have this map, and then I will require these factors here. Okay? So that's a definition of a group. So let me give you examples of those linear algebraic groups. So these are affine linear algebraic groups. So the first example, it's called GLN. Everything is over K, so this is GLN K. And here the collection of polynomials is empty. So, well, let's read this. Whenever you give me a K unital, so it's a polynomial in n square variables, that's where I used n, but it's empty, the collection. So you give me a commutative algebra A, then I'm looking at matrices n by n over A, such that this condition is empty now. So they're invertible. Good, that's GLA, and they satisfy this condition. Why? I don't understand. No, this set is well defined. So this is this set. So I define this set. You give me a collection of polynomials, then this set is uniquely defined. It's the set of all matrices that are in the kernel and are invertible. What it's not clear, so what this condition is requiring is that this set is stable by multiplication. Namely, if you give me two matrices such that they're zero, the polynomials in those matrices is zero, then it's not obvious that the multiplication of the, so fi of g times h is zero. So this condition is requiring that if I have two matrices that are in the kernel of the polynomials, then the products are also in the kernel of the polynomials. And if you have a matrix that is in the kernel of the polynomial, then the inverse is also in the kernel of the polynomials. Oh, that's correct. That's a good one. Thanks. No, I don't need to require that, right? Because if I have, if this condition is if this is a subgroup, right? Then G is, yeah, no, I need to require that the identity is inside. You're absolutely right. That's correct. That's correct. Well, it depends on whether or not subgroup.
I
Yeah, I'm requiring that this is a subgroup, so therefore the identity has to be inside, because I want my group to have identities. So probably I don't need to require this. Yeah, so I hadn't thought about that, but yeah, so I don't need to require it, because the identity has to be in a subgroup. Okay, so GLN is the empty set. So the collection of polynomials that is empty defines me a group, and this group is GLN. The next example is the collection being just one polynomial. So I has only one element, it's a set with only one element, and the polynomial f is the determinant. So notice that whenever you fix a number n, the determinant is a homogeneous polynomial of degree n in n square variables. You have a formula for the determinant. Just expand in rows, and it's a polynomial in these variables which is homogeneous of degree n. And the coefficients are all in the field k. Actually, the coefficients are all in either 1 or minus 1. So the coefficients are in z, if you wish. Right. So the determinant is a polynomial, and there you get a group, and this group is SLN. Okay, and you can check. So here the condition is that the fact that that is satisfied. Well, now you need to look at the kernel of. Oops, that's certainly not a group. The condition is that the determinant minus 1. The determinant is equal to 0 is not a group. So now I need to check the condition, and the condition is, well, if I have a couple of matrices which has determinant 1, I use that the determinant is multiplicative, and then the product of two matrices with determinant 1 has determinant 1. So that's why this condition is satisfied. So that gives me a group. Then the same thing for orthogonal matrices. So if you write the condition A times A transpose is equal to the identity, so this is a polynomial condition. These are polynomials. But now this is a bunch of polynomials. So if you write this in the entries of the matrix A, so you write this identity and you're going to get a bunch of polynomials. How many of them? Well, these are n equations. Right? So for each one of the entries of n square equations. Okay? So these are n square polynomials. But they are all with coefficients in k. So that gives you another example. This is this is going to be the group O of n, On. And if you add to this condition the condition that the determinant is 1, then you get SON. Okay? All right. So that gives me a bunch of groups. And what's the relation between groups and Lie algebras? Right. So now I have, suppose that you have an arbitrary group. So the way I defined it, so the first observation is as follows. So observation, given my definition, a linear algebraic group, a group, linear algebraic group, G is a functor, and this is over K, is a functor from the category of commutative algebras, K algebras, to the category of groups. This functor sends the commutative K algebra A to the group G of A. That was the statement, that if I had a morphism here from A to B, then I get a morphism of groups, GA to GB. And actually, this is a way of defining what an algebraic group is without this condition of being linear. The condition of being linear came from the fact that I'm asking it to be GL of A. So if I just take arbitrary functors from the category of commutative K algebras to groups, but then I need to be a little bit careful about localizations. So I need to add some sort of topology to make sense of this definition better. But that definition there works immediately, just giving polynomials. So that definition makes sure that the groups that I'm defining make sense as just the collection of zeros of a bunch of polynomials. And I can take what I gained with this definition is that I can take coefficients anywhere. So I define at the same time GLN of the complex numbers with GLN of the real numbers, GLN of the rational numbers, and so forth. Okay? But in particular, I can do the following. I can, now if I have a group, G, then I can look at the algebra A to be K polynomials in one variable modulo epsilon squared. So that's a commutative algebra. That's a nice, well-defined commutative algebra. And I can look at what is my group, G of A. So this is now a group. By definition of my group. It's inside of GL of A. Okay? Now, as a K vector space, this guy here is just K plus K epsilon. Right? So any element in G of A, this can be written. So if I have an element G inside of here, I can write this guy as an element, let me say, G1 plus epsilon G2, where now Gi is a matrix n by n with coefficients in K. Right? Any n by n matrix with coefficients in A can be written this way, uniquely. Okay? In other words, okay? All right. So now I may ask, what is the collection? I'll define it this way. The definition is the Lie algebra of the group G. This is a K linear vector space, and this consists of all the elements X, which are n by n matrices with coefficients in K, such that the identity plus epsilon times X is inside of G of that algebra A. Yeah.
In this time, we take the I empty because it seems that GA depends on the FI, right?
G of A depends on the Fi. That's correct, yes.
In this, since we take I empty.
Why? No, I'm not saying that any matrix, any n by n matrix with coefficients in K, I'm not saying that it belongs here. But I'm saying that any guy that belongs here can be written this way. So it makes sense to say, I'm going to require that G1 is the identity, and I'm going to ask for what are the possible G2s such that this guy belongs here. So that's the definition of the Lie algebra. Is just take G1 to be the identity, take G2 to be an arbitrary n by n matrix. If this combination lives inside of G of A, then I'll say that X lives inside of the Lie algebra of G. So in particular, this is a subspace of GLN of K, which I define to be GL, the Lie algebra GL of Kn. Okay? So now the claim is that this is a Lie algebra. And this is the Lie algebra associated to the Lie group G. Well, to the algebraic group G. I didn't define this as a Lie group. I defined it only as an algebraic group. Okay, so let's check that this is a Lie algebra. All right? So suppose that you give me X and Y elements in Lie of G, Okay? Then I look at the identity plus epsilon x, and this is inside of G of A. And I look at the identity plus epsilon prime of y, and this is inside of G of A, where now I'm looking at this other algebra. K of epsilon prime and then I'll just take the inverses. Let me write first and then I'll explain. So the first observation is this, is that this is a group. And if I have an element of the form, so the first observation is that if x is in the Lie algebra, then minus x is in the Lie algebra. And this is because the identity minus epsilon x is the inverse in the group. You can check this by multiplying these two elements. If you multiply these two elements, you get the identity plus epsilon x minus epsilon x plus epsilon square x squared. But epsilon square is 0 in this algebra. Okay? So therefore, since this element is the inverse of this, and I had a group, this element has to be in the group. Therefore, minus x is in the Lie algebra. So that explains why this guy here is in the Lie algebra and this guy here is in the Lie algebra. Or if you wish, this guy, the whole combination is in the group and this is in the group. These are the inverses of those two. But the problem is I'm taking this product here. And I cannot take product from different places. So in order to make this product to make sense, then I need to understand these elements in some algebra, in some G of some algebra. And what I'll take is the group G of K of epsilon, epsilon prime, and then I'll divide by epsilon square and epsilon prime square. Then we'll see if we need to divide by something more. Okay? So then, if I divide by these ideals, then I know that this guy is in the group, I know that this guy is in the group, and the other two. So now I take the multiplication of these guys. So then this is the identity plus epsilon times some stuff, and epsilon prime some stuff, and epsilon prime some stuff, and so forth. Okay? So what is the coefficient of epsilon here? Of epsilon alone? Right? So then I need to take the identity here, and identity here. And I get x. But then I have another copy from here, which is minus x. So the coefficient of epsilon here is 0. The coefficient of epsilon prime here is 0. The only thing that is missing is epsilon prime. And the coefficient of epsilon times epsilon prime, well, let's check it, is xy minus x, wait, here there's a prime. So it's xy minus xy minus yx plus xy. Okay? So the coefficient of epsilon prime is xy minus yx, which is the bracket of x with y. But now I recognize that in this algebra, I have inside the subalgebra, which is k of epsilon prime divided by epsilon prime squared. Okay? So that sits inside of here. And, well, I have that group, which is G of this algebra. And what I'm checking is that this identity plus this times this is inside of that group. It's inside of G of that algebra. But this is the same thing as G of A. This algebra is isomorphic. Just rename epsilon prime to be epsilon. Therefore, the bracket is inside of Lie of G. Yes?
I don't understand why you cannot write y as epsilon, not epsilon.
Well, because if I just take them on the same algebra, and I make this product, then this product is just the identity. If I had written here epsilon alone, what's the coefficient of, so what you would get the following. You would get the identity plus, let's check. What's the coefficient of epsilon? So if you write this and you write epsilon prime to be epsilon, right? This whole product is just the identity. Remember, we just computed this whole product and we got this expression. Put epsilon prime to be equal to epsilon.
You mean we changed the representation of y?
No. All I'm saying is the following. You're suggesting to put here epsilon instead of epsilon prime.
Yeah, I know. If you just write epsilon, it will be identity.
Right. This will be just, I will get 0 here, and I will get any information. I will not gain any information out of taking this product.
But, according to the definition,
Yeah.
it's nothing about epsilon prime.
Well, no, it does, because what the definition tells me is the following. The definition tells me that I have the following situation. The definition tells me that I have this ring and I have this ring. Of course, these two rings are isomorphic, but I have G of this, therefore I have G of this, and I have G of this. I'll call it A prime, but of course A prime and A are the same thing. But what I do have also is I have this other ring, which is K of epsilon, epsilon prime, divided by epsilon prime square, epsilon prime square. Okay? But epsilon times epsilon prime is not 0 in that ring. And what I have is morphisms from this algebra to this algebra, and from this algebra to this algebra. Right? Just send epsilon to epsilon. It's inside. And epsilon prime to epsilon prime. Therefore, I have, let's call this algebra B. Any element in G of A can be thought of as an element in G of B. And any element in G of A prime can be thought of as an element in G of B. And I also have the algebra, which is A again, but I'll just call it with a different name. Inside of this. And what I've checked is that if I have an element, which is the identity plus epsilon x here, I view it here. The identity plus epsilon y here. Here I'm taking the identity plus epsilon x. I view them both inside of here. I multiply them here. I take the commutator of these two elements inside of here. And what I notice is that it's in the image of this algebra. I know that it has to be an element in G of B. And moreover, it's inside of a subalgebra, which is inside of a subgroup, which is G of this algebra, where epsilon epsilon square is equal to 0.
The question is,
Epsilon prime.
we suppose x, y belongs to a G, right?
I'm sorry? Yeah, I suppose that x and y belong to Lie of G.
The definition of Lie is just that thing. It's not nothing about epsilon prime.
But epsilon prime is just a name, right? So if y is in Lie of G, then by definition the identity plus epsilon y is in G of k epsilon divided by epsilon square. That's the definition of y being the Lie algebra of G, correct? Okay, so now we have an isomorphism of algebras from this algebra to k epsilon prime square, which is an isomorphism. Under this isomorphism, G of this is just epsilon goes to epsilon prime. It's just a different name for epsilon. Under this isomorphism, G of that goes to G of this. And this element goes to the identity plus epsilon prime y, which is an element in this group.
This too is isomorphism, I know, but it's not the same thing, right?
Well, I have different names. I have this algebra, I have this other algebra, and they're isomorphic. And they're canonically isomorphic. Epsilon goes to epsilon prime. That's fine. What's the problem?
You have maybe these two things is isomorphic, but these two different things can be computed.
I don't understand what is the confusion here.
I don't know why you can use this method to prove that.
So I'm a little bit confused as to what is the confusion. So if you want, you can call A and A prime. You can call this A. There's no problem to call this A. So if you call this guy A and you put epsilon here, okay, and you put here epsilon, but the key point is that I'm taking a product in a different algebra that is larger. So now instead of having epsilon and epsilon prime, here B is going to be the algebra A tensor with A, which is also a commutative algebra. So that's an abstract way of saying this. So if you put G of A and here the same G of A, then I'm mapping A to A tensor A by a morphism that sends an element. So I have two different morphisms here, from A to A tensor A. In here, I'm using the morphism A goes to A tensor 1. And in here, I'm using the morphism A goes to 1 tensor A. So these are morphisms from the algebra A to B. And now I have them abstractly defined instead of using epsilon and epsilon prime. Now, I have an element in G of A, and I have a morphism from A to B. Therefore, I have an element in G of B. I have a morphism in G of A. I have a morphism, element in G of A, a morphism from A to B. Therefore, I have an element in G of B. And now I take the product. But the morphisms I used for X is different than the morphism I used for Y. That's why in this commutator is non-zero. Had I used the same morphism to embed G of A in G of B, namely use the same epsilon in that other language, then I would have taken the commutator to be just the identity. Okay? But the commutator here is non-trivial inside of G of B. And it lands inside of another copy of G of A. And the copy that goes from G of A to G of A here sends A, well, to A tensor A. Okay? All right. So, yeah.
I'm not seeing why identity plus those epsilons is inside G of A.
Oh, because now what I realize is that inside of B tensor B, right? So this algebra here.
That's isomorphic to G of A.
No, this algebra is not isomorphic to G of A.
No, it contains a copy.
Exactly, contains a copy of this.
But I'm not seeing why that identity plus.
Well,
The bracket is.
no, what you know is that this thing here is inside of G of this guy, of this, by definition, right?
Yes.
I took the product, so this is inside of G of this algebra.
Yeah. But why is it inside of G of the other?
Oh, just because there's no, here inside of this, there's no epsilon nor epsilon prime coefficient. So by definition, this guy here.
You have to verify that it's 0 in every polynomial, right? Or not?
That's, I'm sorry? No, because it's a product, right? So I know that this is in the group.
Oh, okay. All right.
It's already in the group, so I don't need to check anything about the polynomials. The only thing is that it's inside of G of this guy instead of being inside of this, and this is only because the coefficient of epsilon and the coefficient of epsilon primes are 0. But this gave me a way, without involving any differential geometry, that whenever you have a bunch of polynomials that cut out a subvariety of GLN in a group, then you know that canonically you have associated a Lie algebra. Let me spend the next 3 minutes. So you can check with this definition that the Lie algebra of GLN is GLN. And that the Lie algebra of ON is what I called ON, and the Lie algebra of SON is what I called SON. And the Lie algebra of I think I defined SLN is SLN. And that these two are the same. But these two groups were different. So you have different groups that may have the same Lie algebra. Okay? But you can check quickly this. That's a nice exercise here. to check that. So this one is nice because it immediately tells you the relation between trace and determinant algebraically. We define this as a kernel of a trace, and this one as a kernel of the determinant. And these other ones tell you, well, just what is to preserve an inner product. So I encourage you to do this exercise. Let me just spend 2 more minutes saying what is an alternative way, which is how you typically would learn these things. Before doing algebraically, you would do this in algebraic geometry, in differential geometry. So in differential geometry, what you define first is you would understand what are manifolds. So smooth manifolds. You just define what the notion, the category of smooth manifolds is. And then you'll ask to have a group element in that category. So that's going to define what a Lie group is. So a Lie group is a manifold with a multiplication that is a smooth map from G times G to G, and an inversion map which is an identity, which is just a marked point, and an inversion map which is smooth. So that's a Lie group. Then the next step is to check that, well, I just told you that the tangent bundle, the vector fields in G, are a Lie algebra. It's a Lie algebra. This I proved. Because this is just the derivations of functions in smooth functions in G. And we check that this is a Lie algebra. But what I can do is look at the action of G in here. So G acts on vector fields by using the multiplication of G with G. And then what you do is, so by either on the left or on the right, I'll just look at the left action. And the next step, so this is the second step, this was the first step. The third step is to look at the vector fields that are invariant by the left action of G. So if your Lie group is connected, well, it doesn't really matter. There's one point, which is the identity, and you look at the connected component of that point, which is the identity, and then you can identify this, the invariant vector fields, with the tangent space at the identity of the group G. Because any vector field, right, you just translate it by the left action of G, and you just get, any vector at this identity, you translate it by the left, and you're going to get a vector field. And inversely, if you have an invariant vector field, just take the value at the identity. Now, the theorem to prove is that this inside of all vector fields is a sub-Lie algebra. And this is non-trivial. So you need to check that if you have a vector field that is invariant on the left, and you have 2 of those, you take the bracket, you're left with an invariant vector field. So that's an exercise in differential geometry. So now the beauty of that proof there is that this statement is the definition of Lie of G. Is equal to either of these 2 spaces with that bracket. Okay? So now, the beauty of this definition is that all the groups that I defined today are smooth manifolds. If you take K to be the real numbers, or if you take K to be the complex numbers, every group that I defined today, these are polynomials. You can check that the zeros are regular values for this polynomial. So the inverse function theorem tells you that those are smooth manifolds. And the exercise that is non-trivial, perhaps, is to this algebraic definition that involves some epsilon squared being 0 gives you the same Lie algebra than those. Okay? So in principle, you need to understand what is the connection between these 2. So I'll talk a little bit about Lie groups next time. All right. Yeah. All right.